Okay, so while we are waiting, if anybody has any questions, please go ahead. Let's just wait maybe 1 or 2 minutes more, and then we'll begin. Okay, so let's begin. Today we will discuss perhaps one of the most important algorithms in quantum computing that forms an essential ingredient to many other algorithms that are, composed by putting various parts together. And this algorithm that we will discuss today is for computing the Fourier transform. It's called quantum Fourier transform, but essentially it transforms one, quantity into another exactly the same way as the classical Fourier transform works. And just as the classical Fourier transform is very useful in solving a lot of problems, for example, it can convert convolution integrals to product integral, and if there are phase delays in one domain by Fourier transform, you can go to another domain and you can multiply with that number and so on. And in quantum computing, the Fourier transform algorithm is actually very important, not in its own right, but also as part of other more complicated algorithm. For example, Shor's factoring algorithm that is able to solve the prime factorization problem in polynomial time instead of exponential time. That is basically a Fourier transform algorithm combined with the phase estimation algorithm. So our tomorrow's lecture would be phase estimation and today's would be Fourier transform algorithm. These two combine to form many various algorithms. For example, yesterday we were discussing about the Grover's algorithm, that it has this one drawback that we have to know the value of R before we even apply the Grover algorithm, which is dependent on the number of solutions in the search space. So those solution counting is actually done by using a quantum Fourier and quantum phase estimation algorithm in tandem. It's called quantum counting. Similarly, like Shor's factoring algorithm is nothing but a Fourier transform and a phase estimation algorithm in tandem for a particular unitary operator for phase estimation. And similarly, this Fourier transform algorithm is the key ingredient in one of the fundamental problem for quantum computing, which is simulating quantum system itself. For example, you have an atom with few electrons around it, and you want to find out what is its ground state energy or ground state, etc. Or maybe we want to study dynamics of molecule formation of different atoms and so on. So the evolution of all of these quantum systems, they are actually based on quantum Fourier and quantum phase estimation algorithms. So in today's and tomorrow's lecture, we will be able to understand these two basic algorithms. Of course, it's not going to be possible in this course to discuss all of these advanced algorithms, but you can easily understand those algorithms based on these two that we are going to study. So let me begin today with the Fourier transform algorithm, and then tomorrow we will focus on the phase estimation part. Let me share my screen. All right, so today we are going to develop an algorithm and a circuit for the Fourier transform. And as I inquired from all of you that, I guessed that all of you are familiar with the usual Fourier transform anyway, so I'm not going to spend much time on that. Okay, so Fourier transform is essentially a change of basis. Just like in classical, Fourier transform, we imagine Fourier transform to be, a change of domain. If we are working with some function in, let's say, in the spatial domain by Fourier transform, we can go to the frequency domain and so on. And there are a lot of different, type of conjugate domains that you can transform from one to the other and vice versa. So similarly, in quantum computing, we think of a Fourier transform as, a sort of a change of a basis. But its application actually rely on its, usual interpretation as well. So this is a change of basis in such a way that, let's say, if we have some vector, some state J, and we apply the quantum Fourier transform to it, this goes to a new state, and which is given by some k is equal to 1 to n exponential 2 pi iota j k divided by n sum over all possible states, where this j is a decimal number and this k is also a decimal number, and this n is the number of possible states. So if we are talking about a number that can be represented by n qubits, then capital N is 2 power n, and this number j is essentially, if I write it, j1 j2 all the way to jn. So this j is j1 into 2 power n minus 1 plus j2 into 2 power n minus 2 all the way to jn 2 power 0. And for example, if we have a number 101, if this is the state j that we are talking about, so for this state the value of sort of the decimal representation of this state j is 1 into 2 power 2 power 2 plus, because it's n minus 1, 0 into 2 plus 1 into 2 power 0, which is 1 into 4 plus 0 plus 1 is equal to 5. So this 101 in binary goes to 5 in decimal. Similarly, this k is the decimal value sort of this state k, where k will also be represented as k1 k2 all the way to kn, and this number k is k1 into 2 power n minus 1, k2 into 2 power n minus 2 all the way to kn into 2 power 0. You might notice that today I have changed my notations of bits little bit, and I'm labeling this leftmost qubit as k1 with index 1, and then index 2 and all the way to index n, instead of my usual labeling that I used to use x as x naught, x1 all the way to xn minus 1. This is helpful because of easier transformation to Python, because Python index is 0, 1, 2. So I'm changing this notation a little bit today, because that will make our life easier when we work with different sums and multiplications. But of course, you can easily work everything out if you label these states again from 0 to n minus 1. That doesn't matter in terms of overall algorithm, but it makes things a bit more complicated. So that's why I'm labeling my state state qubits from 1 to n instead of 0 to n minus 1. Okay, sorry, this k, however, since this magnitude can be 0 to n minus 1, so this is 0 to n minus 1, because for state 0, 0, 0, this number k would be 0, and for the state with all bits in one state, this would be n minus 1. Okay, so with this definition, so QFT has been defined as an operation that will transform a state j to another state which is given by this. Okay, so I'm not going to prove it, but it can be an exercise for those of you who have maybe a physics background or maths background, that you can show that this these QFT and J, they form an orthonormal basis set. That just as we can represent any n-bit state using a superposition of k's, we can represent that n-bit state using a superposition of these QFT J's as well. we can call them, some Q. So this Q state, they form an orthonormal set as well, which means that if I write this as Q, then Q prime Q, they form their inner product gives a delta function, which means that which is 1 when Q is equal to Q prime, and it's 0 when Q is not equal to Q prime, which also means that I can represent, any general state, I don't know, let's call it some A, as some superposition of these states Q. So equivalently, we can represent this A as this original computational basis state, but we can also represent using this Fourier transform basis state. Okay, so these orthonormality will be apparent when we implement it graph on Python as well. Okay, so let me, before I develop a circuit for before I develop a circuit that does this transformation, let me say a few more words about this particular choice of this definition. Okay, and for that, let's say that I have a general state phi written as some j0 to n minus 1 as some aj j. So this is written as superposition of these computational basis states. So if I apply, let's say, a QFT and this state phi, which means that, and let's call it some state psi. So this QFT will go right to this J state, and this this definition that we have adopted, this one, this works like this, that QFT and this state J will give us this. So let me put this thing here. So this will become sum over J from 0 to n minus 1, AJ 1 over n square root, sum over K from 0 to n minus 1, e power 2 pi iota j k over n, sum over k. And let's interchange the sum. Let's bring this sum over k out, and whatever is left is, let's say we put it inside. So this is sum aj 1 over n square root exponential 2 pi iota j k over n into k. And let's call this thing, some bk, where bk is this, that bk is 1 over n factor n square root sum over aj exponential 2 pi iota jk over n. So this is a classical computation, that there are some number aj's, and you can think of it like this. For example, you have a signal which has a length of n. So it starts at 0. There is some value, let's say it's a function like this. So these coefficients, let's say they are aj's. So their Fourier transform, DFT, which is implemented using several different type of fast Fourier transform algorithms, the DFT of this discrete signal, which technically DFT is the discretized version of the Fourier transform of the discrete signal. So this is a discrete signal. Its Fourier transform in general is a continuous function. But if you discretize that Fourier transform again, so you go from the discrete signal to the discrete signal. So this DFT, the coefficients of this discretized function, they are exactly given by this expression. So this BK, this definition actually is the definition of the discrete Fourier transform. So the way this transformation is chosen is such that when it is applied to any general state psi, its coefficients aj, they transform according to the df, the classical dft. Of course the basis is changed as well. Here the basis is j, here the basis is k. So there's a change of basis and there's a change of coefficients. The coefficients are changing according to the classical discrete Fourier transform. So that is actually precisely the reason why this particular definition for the quantum Fourier transform has been chosen. Okay, so let's now get back to this thing again. After motivating you that this transformation reproduces the usual discrete Fourier transform that we study for discretized functions. And let's now work out the circuit that should implement this Fourier transform. So circuit or algorithm. Any question so far about the definition of Fourier transform? No? Okay. So let me rewrite the definition here again. So let's say that we have some state q, which is the qft of some state j, where this q is, just to recall, is q1 q2 up to qn, and the qft, and this j state is nothing but j1 j2 all the way to jn, which means that if we have some j1 j2 all the way to jn, we want an algorithm or a circuit which gives us at the output q1 q2 up to q. Okay, and the transformation of a particular j to q is given by this. So q is 1 over n square root sum of from k is equal to 0 to n minus 1, where n is 2 power n, and exponential 2 pi iota j k divided by n k. So this is the function that we want at the output. All right, so let me write it like this. So I'm just going to be a little bit on the left side. So q is 1 over n square root sum over k from 0 to n minus 1 exponential. Let me write this exponential as exp. So now this is 2 pi iota, and for the j, let's write it j, and for n I'm writing 2 power n, but for this k let's insert its definition. K is nothing but kl 2 power n minus l, where l goes from 1 to n. This is in exponential, and then this multiplies k. So this particular definition of k is the one that I already wrote. Okay, k was k1 into 2 power n minus 1, k2 into 2 power n minus 2, all the way to kn into 2 power 0. So I can write it in a combined fashion like this. All right, so now I can, it's just going to be one manipulation after the other, where we're not going to do any mathematics or anything. I'm just going to rewrite all of this thing in a particular way. So exponential 2 pi iota j, let's take this 2 power n inside. So when this 2 power n comes under this, So this 2 power n cancels away, and our sum is only from L1 to n KL 2 power minus L. So this 2 power n is gone with this. And now I have this thing. All right. So this exponential is something like this, exponential 2 pi iota j sum k1 exponential 2 power minus 1 plus 2 pi iota j k2 2 power minus 2 and so on. So this sum indicates that there are these terms that are adding up. So it means that I can write this sum as a product function, because in product the powers add, so we can write it. So there is this sum from k0 to n minus 1 on the outside, but over here it's now a product from n1, L is equal to 1 to n of exponential 2 pi iota j kl 2 power minus L. Okay, so I turned this exponential, this product into this sum into the product of these exponentials, because this product and this tensor product mean that all of this term, if there is any quantum state that will soon bring this thing in, they have to be product in according to tensor rules. Okay, so this k state, now what we have on the outside, this sum over k is nothing but is something like this. And actually, let me just write this 1 over n as 2 power n square root, and this sum over k is basically sum over k1 from 0 to 1, sum over k2 from 0 to 1, sum over k3 from 0 to 1, all the way to sum over kn from 0 to 1, L1 to n exponential 2 pi iota j k L 2 minus L, where this k is now going to be written k1, k2 all the way to kn. This is something that we have already discussed, that this k0 to n minus 1 essentially means that alternating the values of all of these qubits to 0 and 1. Okay, so let's now rewrite it like this, that I have this 1 over 2 square root, and let me make all of this like power n. This n which is here, I'm taking it out. Now this sum over all of these terms, this can be written in an overall product like this, that I can go from L1 to n exponential 2 pi iota j kl 2 power minus L k sub L. So this thing that I have written is exactly the same as the thing on the top, because this product from of all the terms from L1 to n, this will result into this, because this product is already this, but this sum that is written over here is essentially the product of these different kl terms, because this k1 k2 kn is nothing but k1 product k2 all the way. So, and there is a I'm forgetting one thing over here, which is there's a sum over kl from 0 to 1. So all of these sums that are outside, I can take this sum inside, because now my kl is inside this term. So all of these things are now taken care of. So I first take this sum over kl from 0 to 1, that this kl can be 0 and 1, and then all of these terms get multiplied, which is equivalent to multiplying first and then interchanging all of these bits. Is everybody okay with this step? All right, so let me write it like this, and then let me expand it if you want. And so this essentially means this, that I have, the first term sum over k1 from 0 to 1 exponential 2 pi iota jk1 2 power minus 1 k1. So this answer sum over k2 from 0 to 1 exponential 2 pi iota j k2 2 power minus 2 k2 all the way to the last term. So kn from 0 to 1 exponential 2 pi iota j kn 2 power minus n kn. So this tensor product means that I can write this term one by one because each one of them corresponds to the qubit. Okay, so let's now expand each of this sum. So this is 1 over 2 square root power n, and let me take this 1 over 2 square root with each of this term because I have n terms. So this 2 square root comes with this thing, so this becomes 2 square root, and this sum from k1 is equal to 0 or 1. So when k1 is 0, this k1 is 0, exponential 0 is 1. So I have this 0 plus exponential when k1 is 1. So this k1 becomes 1. So I get 2 pi iota j 2 power minus 1 1. So this is the state of the first qubit, and then the second one over here is 0. When k2 is 0, this exponential becomes 0. So exponential 0 is 1. So 0 comes as it is, plus exponential 2 pi iota j 2 power minus 2 k2 2 square root. Similarly, the next term would be 0 plus exponential 2 pi iota j 2 power minus 3. So this is 1 square root. And the last term would be something like 0 plus exponential 2 pi iota j 2 power minus n 1 over square root. So this is how all of these, qubits have been written at the end. So I haven't really done anything. I just wrote this, initial definition. So this definition, I just, manipulated it, put different terms in different ways and rearranged it in this final form. Let's now see how I can get this term, because this is my Q1. So if you want to label, since Q is Q1, Q2 all the way to Qn. So Q1, so this is Q1. So this state is Q2, this is Q3, and all the way to Qn. So let me first work out what is the circuit for Q1. So this Q1 state is 0 plus exponential 2 pi iota j over 2 1 into square root. Let me go back here again. You see, this is j 2 power minus 1. So I brought this 2 under j. So this is this Q1 state. So essentially we need a phase gate which applies a phase j by 2 into 2 pi to this one state. But we can actually do a little bit better, because for the next term we will need a phase gate which applies a different phase, and so on. So we will need n different types of phase gates over here implemented on each of the qubit, and which are controlled by all inputs, because this J is going to be computed using all the bits of the input state, because this J is nothing but so this J is this state, so it comes from this state. So if you have to apply a phase which is dependent on J, so we need to have a controlled phase operation which is controlled by each of the qubit, and then we have to have different type of phase controls for each qubit. But we can actually see one very important thing, and we will see that our requirement for gates would be simplified, and that I can see just from this number exponential 2 pi iota j. This e power 2 pi iota j by 2 can be written like this: 2 pi iota 1, and for j, let me put the definition for j. So j is nothing but j1 into 2 power n divided by 2. This 2 is coming, plus j2, sorry, there's an n minus 1, into 2 power n minus 2, and there's this 2 which is coming from outside, j3, 2 power n minus 3, 2, all the way to, let's say, jn minus 1 into 2 by 2 plus jn 2 power 0 divided by 2. Now we see that this number is going to be an integer, because this j1 is integer, and this is like 2 power n minus 1, and let's say n is 3. So this is 2 power 2, which is 2 square 4, and 4 divided by 2 is an integer. So if this is 3, so 3 minus 2 is 1. So 2 goes with 2. This is still integer. So this is integer. This is integer. This is going to be integer all the way except for the last term, because last term is this jn integer, and this 2 power 0 is 1. So this is going to be either 0 over 2 or 1 over 2. So this is non-integer, and we know that exponential 2 pi iota any integer m is 1. So it means this phase is actually just equal to 2 pi iota jn by 2. That the phase, this phase is now only dependent on the last qubit of the J state instead of every qubit. And this, by the way, will be equal to 0 if jn is equal to 0, and this would be equal to, if jn is 1, this 2 goes with 2. So I have exponential pi iota, which is, sorry, this would be equal to 1 when jn is 0, and this will be equal to minus 1 when jn is 1. So it means that at least getting q1 is now very easy, because this all I have to do is make sure that this number is plus 1 when jn is 0. So let me just write straight again. So q1 has been found to be 0 plus exponential 2 pi iota into jn by 2, 1 by 2, which is equal to 0 plus 1 by square root 2 when jn 0, and 0 minus 1 square root 2 when jn is 1. So what gate can give us this depending on jn? A Hadamard gate. If I just apply a Hadamard gate to the nth qubit of my input, I get the first qubit of my required output. Because this is the first qubit, it is depending on the nth qubit. And it only needs a Hadamard gate, because this is given by Hadamard, this is given by Hadamard when it is applied to 0 and 1 respectively. Okay, so the first qubit, is worked out. So let me sort of draw a circuit here. So let's say this is J1, J2, all the way to Jn. So at least I have been able to find Q1 that it only requires a Hadamard on Jn. So let's say a Hadamard, and whatever comes here is my Q1. Okay, so Q1 is taken care of. And let's see what Q2 is. So Q2 is this. It is exponential 2 pi iota j to power minus 2. So let's work out Q2. So Q2 is 0 plus exponential 2 pi iota j over 4, or let me just write it, 2 power 2 into 1 over square root. Now this exponential 2 pi iota j over 2 power 2 can be written as exponential 2 pi iota, and this j is j1 2 power n minus 1 over 2 power 2 plus j2 2 power n minus 2 2 power 2 all the way to, let's say, jn minus 1 2 power 1 over 2 power 2 plus jn 2 power 2 into 1, because 1 is 2 power 0. Now in this case, this is going to give us an integer, this is going to give us an integer all the way to this term except this, because this is 2 power 1 and this is 2 power 2, so this is 2 divided by 4. So this number is jn minus 1 by 2, and this number is jn divided by 4. So this, can be deleted. This can be deleted because exponential 2 pi iota into integer is 1. So this is nothing but exponential 2 pi iota jn minus 1 over 2 plus jn over 2 power 2. So it means that I can get my Q2 state by this thing. So this jn minus 1 by 2 is just a Hadamard again, because this 2 can be cancelled. So let me write it like this. So this is, exponential pi iota jn minus 1 when it multiplies with this and into exponential, uh, 2 pi over 2 square iota jn. So basically, what we need is a situation that we give a controlled phase to this one qubit, which is going to be, work like this. That I can always do this thing by using a Hadamard on jn minus 1. So if my jn minus 1 bit is 0, so this doesn't need to be applied. And if my jn minus 1 bit is 1, then I need a phase of minus 1, which is equivalent to applying a Hadamard on jn minus 1. For this thing, however, I will need a gate which gives us a required phase. So this phase becomes, so this should be controlled by jn, that when jn is 0, no phase, and when jn is 1, I need a phase phi is equal to, 2 pi over 2 square, which is pi over 2. So it means that for my qubit Q2, what I can do is, for the jn minus 1, all I need to do is apply a Hadamard on it, which will, work for this part, because this Hadamard is essentially a phase gate controlled by jn minus 1. Because when jn minus 1, this will give us 1. When jn minus 1 is 1, this will give us minus 1. Now for the second term, I need something like this, iota pi by 2 into jn. So which means that we need a controlled phase gate which can add a phase pi by 2, but it is controlled by this bit jn, and whatever is at the output, this is my Q2. Now let's see what Q3 is. Where's Q3? Oh, okay. So here's Q3, and I hope that you can begin to see now that Q3 is 0 plus exponential 2 pi iota j 2 power 3 1 over 2 square root, and this is nothing but 0 plus exponential 2 pi iota jn minus 2 over 2 plus jn minus 1 over 4 plus Jn over 8. And over square root of 2. So this is 0 plus exponential iota pi jn minus 2 exponential iota pi by 2 jn minus 1 exponential iota pi by 4 jn minus jn. So I need a phase of pi, which is the Hadamard gate with respect to bit jn minus 2. And then I need a phase gate of pi by 2 controlled by jn minus 1. And then a phase of pi by 4 controlled by jn. But for this one, I can get very easily. I can just apply a Hadamard to jn minus 2. So jn minus 2, let's say jn minus 2. So first I need a Hadamard, and then I need a phase gate that applies a phase of pi by 2 controlled by this state jn minus 1. And then I need a phase gate of pi by 4 controlled by jn, and that is my Q3. And this way we can proceed all the way, and we can see from here that my last bit, which is 2 power minus n, is essentially this, that Qn is 0 plus exponential 2 pi iota j 2 power n 1 0 plus exponential 2 pi iota. So this j would be j1 into 2 power n minus 1 over 2n. So this is just divided by 2. And then for j2, there's going to be multiplying factor of 2 power n minus 2. And when you divide it with 2 power n, this is 2 power 2, and all the way to jn 2 power n 1 square root 2. So this is 0. So now when I take this 2 pi inside, this becomes iota pi j1. Next becomes iota pi by 2 j2, all the way to pi over 2 power n minus 1, because this 2 cancels away into jn 1. So it means I need a controlled phase that give a phase of pi with respect to j1, which I can get just by applying a Hadamard to j1 itself. And then a phase of pi by 2 controlled by j2, because if j2 is 1, this should work. If j2 is 0, this shouldn't be applied. So that's why I need a control with respect to j2, all the way up to jn. So let me add this thing here. So I first need a Hadamard here, then a phase gate of phase pi by 2 controlled by j2, and then the phase gate control of pi by 4 controlled by this one, all the way to the last gate with phase pi over 2 power n minus 1 controlled by this one. And this is going to be my Qn. So similarly, if we have this one, so if you can see the pattern is that you apply Hadamard to this last qubit, you get the first qubit. Then for the second last qubit, you apply Hadamard, and then the phase gate of pi by 2 controlled by the last qubit. Then for the next one, Hadamard, pi by 2, pi by 4, and the control is this. So there is a sort of a symmetric way that we have to apply these controlled phase gates. So a phase gate is something like this, which we can easily see from here. So phase gate of arbitrary phase phi is 1 exponential iota phi 0, because to 0 state it does nothing, and to 1 state it adds this phase exponential iota phi. So in hardware, implementing this phase gate is a really very simple thing. You just have to send a pulse with a particular phase to add this phase. So this phase gate is sort of a primitive gate that can be implemented in most of the quantum computer hardwares. Okay, so there's one trouble, with this algorithm, that we have been able to, perform controlled operations on different qubits, but at the end, Jn has been converted to Q1 and Jn minus 1 to Q2. So there's an opposite way the bits are coming out. So for onward processing and talking, we need a circuit that gives us our final output like this. So far we have been able to reach this point. So this is Qn, this is Qn minus 1, all the way to Q2, Q1. So it means what we will have to do to go to the next, sorry, this goes up, that we will have to apply a swap. We need to swap this qubit with this. We need to swap this qubit with this, and so on. So after the swapping operations, this Q1 goes to the top and Qn goes to the this last part, and so on. So the swap operations are needed when you want your output aligned in the same way as at the input. And let me just compute the total number of operations. So in this circuit, the number of gates that we have is 1 gate here, 2 gate here, 3 gates here, and so on. So it means the total number of gates before swapping are gate count or operation count 1 plus 2 plus 3 all the way to n. And this sum can easily be worked out to n into n plus 1 over 2. Plus, we have to add the number of swap gates. So there's this one swap gate, the second, and so on. So there are n over 2 swap gates, assuming that n is even, but even with the odd number, the order is still the same. So it means our gate count is roughly of the order of n square, because when I multiply this n into n, this is n square, and then there's terms of the order of n. So it means that order of operations in this quantum Fourier transform is n square. And classically, the best algorithm so far that people have been able to discover to implement the discrete Fourier transform actually requires operation of the order of n into 2 power n. So this is increasing exponential in the size of the number of bits for the Fourier transform. So quantum computer can do this Fourier transform operation in polynomial or n square operations as compared to the exponential number of operations required for the classical computation of Fourier transform. So actually, this is the only reason that the Shor's factoring algorithm works in polynomial time as opposed to the classical factoring algorithms that work in exponential number of operations in terms of the number of bits.
Hi sir, I have a question. In classical QFT or fast Fourier transform, what we are talking about is time, the operation to and related to time. However, in QFT, it's all about a number of gates or hardware requirement. So we are not comparing time with hardwares, because in QFT we calculate number of gates, and in classical FFT we calculate time required.
Okay, so no, this operation that I've written, these are number of operations, number of primitive operations that you need, the number of addition, multiplication, etc. And of course, it's not an apple-to-apple comparison right now, but the difference is small. So for example, a quantum gate right now usually takes about a microsecond to implement. but the classical gate can work in like 1 nanosecond. But this difference is still small, because when you work with the huge number of operations, then this small difference is only multiplicative in nature. So the first point is that this is not the time, this is the number of operations. This is also number of operations or number of gates. And of course, the time required for one gate in quantum computing and in classical computing, they are different, but the difference is, not important, because let's say you are talking about n is equal to 1 million. There is a number that can be represented using, 1 million bits, and you want to find its Fourier transform. So quantum mechanically, it will only take, 1 million power 2. But over here, it will take, 10 power 6 into 2 power 10. This 2 power 10 power 6 is, a number that is, even hard to write on this, notebook. So this is still like 10 power 12. So even if there is a time, this one takes, 1 microsecond, and this takes, 1, nanosecond. But if this goes up by the order of, several hundreds of order of magnitude, then this 1 nanosecond doesn't matter. Okay.
Yes, sir. Thank you.
Okay, so let me now show you the implementation that I have worked out. I have already sent this, notebook to you. This is lecture number 7. Let me stop sharing this thing and share. Is there a question over here? Okay, so let me start sharing my computer screen. And this is the notebook number 7 that I have sent you already. You can probably see many complicated implementation of Fourier transform on the web. Here I have tried to, put things in a bit simpler manner. So this, input 1 is just loading of different things. Let me put this thing aside. So let's run this one. And then you see this QFT circuit that I have defined here is a very simple circuit. So let's say it's a quantum circuit with 4 quantum bit and 4 classical bit, and I'm defining it, giving it a name as well, which we can for later calling. And what this circuit is, that it's just starts something like this. So this is QFT4, and first of all, I'm just applying Hadamard to everything. You see, for I in range 4, just apply QFT. So just apply Hadamard on the QFT4 circuit. This QFT4 is a circuit of 4 qubit. So I have written it in such a way that you can easily modify it to work for any number of qubits. All you have to do is just replace this 4 with any number. So you can also define like this 4 as n, and then give n any value. Anyway, so after this Hadamard, what I do, that I have initialized this number p is equal to 0, and for then there's another loop j that goes from I plus 1 to 4, and then there is this counter p plus 1, because I want to give a phase that works like pi over 2 power 1, 2 power 2, 2 power 3, and so on. So that's why in this loop I'm taking this integer 2 over p, where this p is getting incremented each time. So this CP that you see over here is a controlled phase gate. So this is applying the phase to bit I, and the control is in J. So in the first iteration, when I is fixed, so let's say we are talking about this Q naught, and then this control bit is changing from J is equal to 1 to J is equal to 2 to J is equal to 3. And then once I have done all of this thing, I have this barrier for visualization. You can already see this thing here. So this barrier is also within the loop. So I'm applying this barrier after each bit. So this Q naught is being converted to the first, the nth Fourier transform bit, and Q1 is to the n minus first, and so on. And then at the end, I have these swap gates. So these swap gates are essentially just swapping the first ith qubit with 4 minus 1 minus I. So this 4 minus 1 is written because the indexing is only 0 to 3. It's not 0 to 4. It's not 1 to 4. So let's draw it with the MPL matplotlib libraries function. Okay, so here is a circuit, and you can see this is exactly the way I was drawing over there. That this Q naught has these 3 phase gates controlled by the remaining 3 qubits, and so on. Okay, so I'm not using it to run it for any input and output, because it's a general purpose algorithm and we will be using it for different various things. Right now, I want to show you, to give you a visualization of how this works. For example, let's say we have a state which is 0, 1, 1. So if I run it, so you see that this 0, 1, 1 state is this qubit in 0 state, and then this is 1, this is 1, this is 1. So these are the qubit that are up or down, okay, in the computational basis. And then I evolve this SV state that I defined over here from as 0, 1, 1. Let's evolve it under this QFT4 circuit that we just defined over here. This is quantum Fourier transform. And then I plot this new state vector again. So let's see. Now you see this state vector has all its qubit in the XY plane. So in the XY plane, you have one vector like this, the other this, 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 this. So it's a bit harder to see over here because you are seeing it as a 2D computer screen, a representation of the 3D. But what is happening that we have all these qubits at different positions in the XY plane. If you take, let's say, another state 0, 1, 0. So this 0, not 0, 1, 0, 0. And you see this in computational basis, it is either up or down. But when I evolve this state, you again see that I have 4 qubits that are rotating in the XY plane. So essentially, we go from this computational basis to this Fourier basis, in which the vector, the basis vectors are different superpositions of different orientations of individual qubits. So all these qubits are rotating in the XY plane. Okay, so there's another way of plotting it over here, but it's still the same thing. Okay, let me now discuss another circuit, which is the inverse quantum Fourier transform. So this inverse quantum Fourier transform works just as an inverse of the quantum Fourier transform. And for that, let me first just discuss how to work out the inverses in quantum computing, because that's just a little bit tricky. So you have to make sure of something like this. If you have an operator of, let's say, iota a y, its inverse is going to be given by this complex conjugate operation. So this is going to be y conjugate exponential minus iota a. That, if let's say there's this sum operator, so this is also operator this. So first of all, you switch their places, but also don't forget to convert iota to minus iota wherever it comes. So that's why when you apply the inverse quantum Fourier transform, you have to keep track of the sign of the phase as well. Okay, so here you see I have exact sort of reversal of that circuit. So first I'm applying the swap gates, because the inversion of swap is the swap again, and then the inversion of Hadamard is the Hadamard, and then for this qubit, this is the inversion of simply this part, that here we had Hadamard first and phase later, and now we will have phase first and Hadamard later, but also phase is going to be with a minus sign, because the phase operator has exponential iota of phi in it. So when I take its complex conjugate, it becomes minus iota phi. So that's why it's not just you apply phase first and then Hadamard. You apply the negative of phase first and then Hadamard, and so on. Let me plot it, using matplotlib to make it appear slightly better. Okay, so here you see that this circuit is sort of reversal of the this circuit that I have written here. Okay, and just so you know, as a check and also as a practice of combining different parts of quantum algorithm that we build. So it's almost like building subroutines or functions in usual programming. Here, usually we build circuits that do different things, and then we can append these different circuits together. So here, for example, I'm preparing this new circuit identity 4. I'm calling it identity 4. This is a circuit with 4 and I have named it QFTI 4, and I'm specifying that for this quantum circuit, first you append it with QFT4 circuit, and then you append it with IQFT4 circuit, and over here you can specify the qubits where you want to append it. But I just want to append it from 0 to 4, 0 to 3, so it's just being appended from 0 to 3. So let's run it, and this is just a check for myself that if I have built this inverse circuit correctly or not. So I start from state 1001 and I evolve it under this identity circuit identity 4, and let's see, we do this, and you can see that the state is the same as over here as it is over here. So it means that IQFT that we have implemented over here works as it should. You have access to this circuit on your laptops as well, so maybe you want to try it to run it there. Any questions? Okay, so I hope that this Fourier transform circuit is clear, because even though this seems simple, but this forms a sort of one of the most important pillar on which many quantum algorithms are built. Okay, let me now discuss one very important topic that is related to this quantum Fourier transform and also quantum computing in general. So we have been able to see that we can get a quantum Fourier transform much faster using quantum computing than classical computing. So the question is, can this thing be useful? So the answer depends on the way you use QFT. Okay, because the reason is this, that if you have at input some state phi, which is some AJ K, and when you get some state psi by applying a QFT here to this state phi, we already saw that we get something like this, where these BKs are the Fourier transforms of AJ. So we know now that we can perform this Fourier transform from AJ to BK exponentially faster than classical computer. So can we use our classic quantum computer to perform quantum Fourier transform faster than classical computing? The answer is, is that it's actually, if your goal is only to perform quantum computing, you might not have that advantage. And the reason is this: you see, this output state is a superposition state. We don't have access to these individual BKs, because when we will measure, we will either find B1 or B2 or any a single vector, not all of the vectors. So to really find all of these BKs, we will have to make a lot of measurements in not only in computational basis, because when we will make measurements only in computational basis, we will only be able to find these magnitude square of these BKs. Okay, I hope you understand this point, that when we will get different histograms, let's say it's a 2-bit Fourier transform for 0, 0, 1, 0, 0, 1, 1, 1. So these probabilities they are only proportional to bk. So this is, b naught square 1, this is b1 square, b2 square, b3 square. So, and if these aj's are complex, these bk's should be complex numbers. So we don't have access to these complex numbers b's. However, we can still estimate them by first transforming them to another basis and then measuring again. So by doing a lot of computations in computational bases and other bases, we can be able to get these bk's out of this quantum Fourier transform. But by the time we are done with finding these individual bk's after a Fourier transform, the quantum advantage would be lost. So quantum computing, quantum Fourier transform, just for the sake of Fourier transform, will not give us any advantage, most likely. The key of getting advantage from quantum Fourier transform is to use it as part of other algorithms in such a way. Okay, so there is, other algorithm that uses QFT, other things, that at the end, your output is only something that you don't need to make a lot of measurements to find out. Only then you can get the advantage that is being offered by the quantum Fourier transform. And we will see one such circuit, which is called quantum phase estimation, in tomorrow's lecture, where we cleverly use quantum Fourier transform to find something else which would take us, exponential number of steps on a classical computer. I hope that this point is clear, and because we talked about this thing earlier as well, that to get quantum advantage, it's a tricky business because the output is a superposition state, and we don't have access to individual weights of states directly. Okay, is there any questions?
Sir, in simulation, what is the complexity to simulate a single qubit algorithm-wise? Because I'm thinking that.
So to simulate single qubit, you need a single qubit gate, which are 2 by 2 gates. So the complexity is 2 power 1. And to simulate 2 qubits, your gate operations are 4 by 4 matrices. So your complexity is of the order of 2 power 2. So similarly, for n qubit simulation, your complexity is 2 power n. You need exponential number of steps to simulate n qubits quantum on a classical computer.
Sure. Sir, when we say that we don't know the state because it is in a complex position, can we do a simulation and we measure all the, we can see it in block square in simulation instead of going really into quantum computer?
So we can, do that. Let's say right now, I think IBM offers a 32 qubit quantum simulator, up to 30. So on supercomputers, you might be able to simulate like 50 to 100 qubits. But beyond that, simulating becomes an exponentially hard task. And hopefully by the time we have like 400, 500 qubit quantum computer, no classical computer will be able to simulate those results. So there's no advantage in simulating.
Sure, sir. Sir, but when we say a sentence like we don't know the position before we're measuring it, and when we do simulation and we see it in block square, is there any difference in real quantum computer and in simulation? Because we can see it for let's say for a small number of qubits, we can see it in block square. So is not we see it already before in block square without collapsing its state?
Okay, so when we see it, what we mean, let's say it's a state like 0 plus 1 over 2 square root. So if I put it on a block sphere, it's something like this pointing at positive x-axis. But I can see it in terms of simulation. That's my prediction that it's going to be here. And when I actually measure it, I measure either 0 or 1. So it's going to collapse to either 0 or 1. So in this case, and we don't know whether it's going to collapse to 0 or 1. So there is an uncertainty over there. And of course, when we say that we don't know, we're talking about real actual quantum systems. So the simulation assumes, you start with a perfect quantum system, which is, evolving under perfect conditions, and at any point where it is. So that's not a problem. Even, even without quantum computers, we can see this thing from Schrodinger equation using classical computation as well.
Sure, sir. Thanks.
Okay, thank you. So this concludes today's lecture. But